lecture number 13. Okay, so we were discussing about the electric potential, work done, electric potential, and potential difference. Okay, so we shall recall some of the concepts here. So work done. So it is nothing but force into displacement. So it is measured in joules. So basically, the equation is given by like this: initial value to the final value, and force into displacement. And force is nothing but or electric field intensity is nothing but force per charge. So this is how we have taken this one. This next second one. So what we have discussed, uh, work done is positive when it is against the direction of the field. It will be negative when it is in the direction of the field, and work done is independent of the path selected, and work done is zero in a closed contour. That means closed path we have seen. Okay, and potential difference we have seen. So it is nothing but moving the charge from point B to A in the field. So work done in moving unit charge from point B to A in the given electric field. That is known as potential difference. It is given as V, and it is unit charge, moving unit charge from B to A. So therefore, it is B to A minus that is sorry E vector into dl vector, and it is volts and this is joules. Okay, VAB is positive if the work done is uh, against the direction of the field, and it will be negative. It will be work done is that is what is in the direction of the field. So the work done in moving unit discharge from infinity to that point is called the potential at that point, electric potential at that point. The work done moving unit discharge from infinity to that point, it is nothing but electric potential at that point. So the unit is again volts or joules per coulomb, and we have seen the concept of absolute potential also when the potential is measured with respect to a reference. Okay, yes, the potential due to a point charge we have seen, that is V potential due to point charge we have seen, uh, line charge we have seen, surface charge we have seen, and volume charge we have seen. Okay, so let us just recall what all formula we have discussed. And VAB is the potential difference. It is given by Q by 4 pi epsilon naught 1 by RA minus 1 by RB volts. So this is the potential difference between point A and B, where the charge is moving from B to A. Charge is moving from what? B to A. So this is the expression for potential difference between VAB, that is AB, where the charge is moving from B to A in the presence of the field. Okay. Absolute potential means it is nothing but VA, that is simply by Q by 4 pi epsilon naught and RA, and that is measured with respect to reference. Similarly, VB is equal to Q by 4 pi epsilon naught RB. So again, it is work done in moving a unit charge from infinity to point B. Infinity to point B. So your VAB is equal to VA minus VB. VAB is equal to VA minus VB. So this is what we have discussed. And absolute potential also we have discussed. And when charge, this is at the origin, you can also find potential, and also find potential, that is the V of R, or at point A, when charge is not at the origin, that is Q by 4 pi epsilon naught R minus R dash, or it is Q by 4 pi epsilon naught RA, where you have got origin here, okay, and Q is at this point, and I am measuring potential at A here. So this is R dash, and this is R, and this is R minus R dash. It is only a scalar quantity, only a magnitude, that's all. Okay. So this is a potential due to point charge, so which is not located at the origin. Okay. And you are finding potential at a point due to that point charge. Okay. And if you have got more charges like that, that also we have discussed. So VA is equal to V of R, that is equal to summation of I is equal to 1 to N is Qi by 4 pi epsilon naught R minus Ri. This goes on increasing. I is number of charges present, and the reference point of zero potential is always assumed to be what? Infinity. It is a reference point of zero potential is nothing but infinity. Okay, so this is what we have discussed so far. And if reference is not, if reference is not infinity, so what is that you have to do? Very simple. So you just have to use the same relationship. So it is RA, and you have to use the one constant. That constant has to be determined um, at chosen reference point. At chosen reference point where where V is equal to 0. You have to find that. You have to find C at V is equal to 0. So potential difference between these 2 points is not function of C here. So the potential difference between these 2 points is not function of C, and it has to be calculated. We shall solve problem on these things. Okay, and we have discussed about the potential due to line charge at a point A, that is V of R, that is in line integral. So rho L of that is dl divided by 4 pi epsilon naught, and is R. That is the distance between um, the point A as well as the line charge, where R is equal to R minus R dash. So this is potential due to line charge. So on surface charge, so it is again VA, V of R, surface integral rho s by rho s of R dash, that is ds divided by 4 pi epsilon naught r. So this is a surface charge. Okay. Next, you want to recall that formula for volume charge. So the volume charge VA is equal to V of R, volume integral rho V of R dash into dV divided by 4 pi epsilon R minus R dash or simply R. So this is a volume charge. Okay. So these things are very much important in finding different potentials due to different kinds of charges. Okay. Yes. So we have started solving some numericals. So before moving on to numericals, we shall discuss one concept and come back to solving the numericals. The next concept is concept of equipotential surfaces. Equipotential surfaces. So the name itself says equipotential. Uh, there will be many points at which the electric potential is same. Those points are nothing but equipotential points, and the potential is a scalar quantity, and it depends on the distance between the point at which the potential is to be obtained and the location of the charge. Okay, so there can be any number of points where the distance is same, and there exists some potential which will be equal at all points where the distance is same. Those points are nothing but equipotential points, and the surface is called as equipotential surface. Okay, so an equipotential surface is an imaginary surface in an electric field, so in which all points on the surface are at same electric potential. So for example, here I take a charge like this Q, and I will mark like this a circle around it of radius R1. Okay, and I'll mark few points A, B, C, and D. Okay, the radius of the imaginary circle is R1, and the point A, point B, C, D are at the same distance from the charge Q, which is at the center of the circle. Therefore, A, B, C, D are having same potentials because their distance from the charges are same. Therefore, you can call that as equipotential surfaces. That means the work done in moving the charge from infinity to that point, uh, can be A, B, C, D, will be same because they are under the influence of the charge, same charge Q at same distance R1 from Q. So this is nothing but equipotential points. You can have one more imaginary surface like this, imaginary circle like this, and let the radius be R2, and let the points be A dash, B dash, C dash, and D dash. Now A, B, C, D, A dash, B dash, C dash, D dash are at same distance from Q. That means they are the distance of R2 from the origin. Therefore, A dash, B dash, C dash, D dash are under the influence of same electric field which is produced by the charge, and they are the same distance from the charge. Therefore, the potential at those points are at same value, and you can also call this as equipotential surfaces. So, for example, here, so you can mark like this. So, this is the equipotential surface 1, and this is another equipotential surface 2. Okay, so this is how the equipotential surface exists in systems. Okay, so you will get some surfaces where the potentials are same when you traverse around it. When you traverse around it, the work done will be same on that surfaces. Okay, so what happens to the potential? What happens to the potential as you move away from the charges? So we just use that expression that V is equal to Q by 4 pi epsilon naught R. So, so when you move away from the charge, the potential decreases. The distance increases, the potential decreases. That means the voltage will be very much high, or the potential will be very much high when it is closer to the charges, and it will be very much lesser when it is moving away from the charges because the field decreases. So therefore, the potential of equipotential surfaces goes on decreases. Okay, so this is what the another concept, very important concept. So, so if it is clear for you, you can type 0 on the chat box. I will move further. Okay. Yes, we shall solve some problems and then come back to concept again. Right on the problem. A point charge a point charge of 6 nanocoulomb. Point charge of 6 nanocoulomb is located at origin in free space. It is located at origin in free space. Find Vp at P is equal to zero point 0.2 minus zero point 0.4 and 0.4 when V is 0 at infinity and when V is 0 at 1 comma 0 0 and V is 20 at 0.5 1 minus 1. Okay, just I'll leave this slide for a few minutes. Just go through this problem, comprehend what is given, and comprehend what is to be found out. Okay, so what is given here? So point charge of Q is equal to 6 nanocoulomb is located at origin, and it is generating the electric field. Due to that electric field, there will be some potentials, and you are required to find the potential at point P. Okay, under three cases. That is when the reference potential is assumed to be at infinity, and the reference potential is assumed to be at 1 comma 0 comma 0, and you are required to find the potential at P due to an voltage of 20 volts at point 5 1 comma 1 comma minus 1. This is what you are supposed to find out. Okay, so this is the first one is classic case, second one is reference is not at infinity, third one again is reference not at infinity. So let us solve one by one. Okay, so let me find Vp, formula Q by 4 pi epsilon naught r minus r dash. Okay, so it is r minus r dash is square root of it is the Q is at 0 comma 0 comma 0, and P is at point 0.2 comma point 0.4 comma point 0.4. Okay, so this is what we have got now. So it is 0.2 square and 0.4 square and 0.4 square. It is 0.6. Therefore, Vp is equal to answer. Yes, solve it and get me the answer quickly.
$89.85. 85.
89.85 volts. Okay, this is when reference is at infinity. Okay, yes. Next, we shall move on when reference is not at infinity but at 1 comma 0 comma 0. This is the case. So the formula gets changes here. Q by 4 pi epsilon r minus ri plus C. You are supposed to find the voltage at P due to the reference given to be at 1, 0, 0. So let us solve for C first. Okay. So this is the expression we have to use. Let us find C when voltage is 0. Okay. So let us move ahead to find C here. So reference voltage is R, VR. So that is Q by 4 pi epsilon naught R minus R reference plus C. Okay. So R minus RR, it is given as square root of 1 minus 0 square, 0 minus 0 square, and 0 minus 0 square. Because Q is at this point and reference is at 1, 0, 0. Therefore, we will be solving for C here. That C will turn out to be minus 53.9. It is a constant value. Okay. Using this C, you can solve for the potential at P. Okay. So Vp is equal to Q by 4 pi epsilon naught R minus Ri plus C, and substitute. So here R minus Ri, just solve here. R minus Ri, square root of again uh, it is 0.2 minus 0 square, it is 0.4 square plus 0.4 square. Okay, and here C is given to be or solved to be 53.92, and solve for Vp. Yes, it is 0.6. Solve for Vp.
Sir, 36 volts.
36.
6.
Okay. Just check out the potential got changed due to change in the reference. Okay, 36 volts now. Next, last case. So V is 20 volts at minus 0.5, 1 minus 1. So when V is 20 volts at minus 0.5, 1 comma minus 1, what is Vp? That is a question. It is a question. Okay. So let me have the Q, let me have P, and let me have one more point, for example, K here. The K is voltage, 20 volts. Okay, the K coordinates are minus 0.5, 1 minus 1. Okay, so this is 0, 0, 0. So again, it has to be found out when reference is not at infinity. You have to use the same relationship, that is Vp is equal to Q by 4 pi epsilon naught R minus R dash or Ri. So plus C. Find C. Okay. Find C for V is equal to 20 volts, and then substitute back, you will get the answer. Okay. Yes. To find C, that is Vk is equal to Q by 4 pi epsilon naught 4 pi epsilon naught R minus Rk plus C. R minus Rk is given to be minus 0.5 minus 0 whole square, 1 minus 0 square, minus 1 minus 0 square. That turns out to be 1.5. And we know Vk, that is value is 20 volts. Substitute C or solve for C, you will get it as minus 15.9 something. Just check out this one.
Yes, sir. Correct, sir. Minus 15.97.
Okay, minus 15.97. Yes, use this one in the standard expression. Q by 4 pi epsilon naught R minus R dash plus C. R minus R dash is same as before. It is 0.2 square plus 0.4 square, 0.4 square, that is this 0.6. And you can solve for Vp using the C. Yes, answer
70.94.
70.
3.94 volt.
94 volts. Okay. Yes, if this numerical is clear for you, please type 0 on the chat box. Now, so we shall move on further. Potential difference concept again. Potential difference due to infinite line charge. Infinite line charge. Yes. So we have got a y-axis, x-axis, z-axis, and I have got infinite line charge along the z-axis. Okay, and that is rho L coulombs per meter, and I am interested I'm interested in finding potential difference between A and B. Potential difference between A and B. Okay, due to this infinite line charge, and this is RA, radial distance from the infinite line charge RA, and this is RB, radial distance from infinite line charge, that is RB. So it is radially located points A as well as B. What is electric field intensity due to infinite line charge? Can you just recall?
So rho L by 2 pi epsilon.
Exactly. Rho L by 2 pi epsilon naught R, and it will be in the direction of uh, radial vector. Okay. So your potential difference now, VAB is equal to B to A minus E vector into DL vector. So DL vector is given to be the distance vector. Distance vector will be along the radius, that is radially. So it is nothing but dr into AR cap, dr into AR cap. So I will just take this one onto the next slide. So VAB is equal to minus B to A. It is E vector into DL vector. Therefore, minus B to A, E vector into dr into AR vector, unit vector. And E vector we know it is Q by 4 pi epsilon R, okay, into AR vector into dr into AR cap. So therefore we'll be getting minus B to A Q by 4 pi epsilon naught 1 by R dr. So this is what you get. So 2 pi epsilon. So 2 pi epsilon, 2 pi epsilon. So integration of 1 by R.
Log of.
Yes, natural log. So it is royal by, it is royal by, sorry, it's royal, and this is royal. So royal by 2 pi epsilon naught minus, okay, so natural log of R, limits RA to RB, RA to RB, and if you use it, so royal by 2 pi epsilon naught, natural log of RB by RA. So this is the expression for potential difference between A and B due to infinite line charge. Infinite line charge. Okay. Yes. Volts. So you can also extend this to an infinite sheet of charge. That is also possible. And this is a standard result. So it can be used to find potential difference between any two points in the electric field due to this infinite line charge. Okay. And let us solve one more problem here based on this concept. Yes. Two uniform charges two uniform charges, uniform line charges, 8 nanocoulomb per meter, are at x is equal to 1 and z is equal to 2, and x is equal to minus 1 and y is equal to 2. X is equal to minus 1, y is equal to 2. There are two line charges, 8 coulomb per meter. One is situated at x is equal to 1 and z is equal to 2. Okay, which plane it is? Which is this plane and which is this plane? X is equal to 1 and z is equal to 2. So y is varying. Okay, so y is varying and here z is varying. Okay, yes. So you are supposed to find. You are supposed to find v at p, where p is 4, 1, comma 3. Okay, given. Okay, potential at origin. So VO is equal to what? 100 volts. Potential at origin is going to be what? 100 volts. Yes. So just go through the details, what is given and what is to be found out. So I got two line charges located x is equal to 1 and z is equal to 2. So that means you are having a line, which is at a distance of 1 units on the x-axis, and you're having and it is at the height of 2 units on z-axis. Okay. Similarly, you're having one more line which is at a distance of minus 1 units on x-axis and 2 units on y-axis. Okay, and you are supposed to find the voltage at P, and given the voltage at the origin is 100 volts. Origin is at 100 volts. Yes. Let us write the line charges. So Z, Y, X minus X. Okay. X is equal to 1 and Z is equal to 2. So let X be equal to here 1 and height here 2. Okay. So you will be having one line x is equal to 1 and y is equal to 2. So this is what an infinite line charge. Infinite line charge. This distance is what? 1, and this distance is what? 2. Okay. Yes. Any doubts, sir? If this is clear for you, type 0 in the chat box. Yes. Next, we'll be having one more line charge, that is at x is equal to minus 1. So let the point be here -1 and y is equal to 2. So y is equal to 2. So let be here -1 and y is equal to 2. That means x is constant, y is constant, so z is variable. So I have to drop a point like this. Okay. So this will be -1 and this will be 2. So it is infinite. It is understood that it is infinite. Yes. Now rho L is given how much it is 8 nanocoulomb per meter, and this also rho L is 8 nanocoulomb per meter. Okay. Now you are having one more, this one, the potential is V is 100 at origin. Yes. So now, so you have to obtain potential difference. Obtain potential difference. Potential difference. The P. The P is where is the P? P is at 4, 1, 3. So P somewhere here. I will just mark it. 4, 1, 3. P. 4, 1, 3. So you're supposed to find out the potential at P due to this two line charges, the red color one and the green color one. Okay. Yes. Line charge one, we can potential difference VPO. So VPO due to line charge one, you can find out, and VPO2 due to line charge 2 you can find out and add it, you will get VPO1, okay, or VP1 directly. Okay. Yes, similarly you can do it. Yes, let us solve for VPO1. That is nothing but potential difference due to line charge 1, that is rho L by 2 pi epsilon naught. So logarithm of so RO1 divided by RP1. So RO1 divided by RP1. So RO1 is nothing but so 1 square plus 2 square root 5. So how it is 1 square and 2 square? It is 1 minus 0 and 2 minus 0. It is x is equal to 1 and z is equal to 2, and y is at 0, 0, 0. Okay, that is how. And RP1, RP1, again you have to take x coordinates as well as z coordinates. So 1 minus 4 square, okay, and 2 minus 3 square. 2 minus 3 square, that is equal to root 10. So I'm just your p is at this point. So just take this one, p from x coordinates and z coordinates only, and then solve for this one. And you'll be getting for VPO1. VPO1, so that is equal to minus 49.83, minus 49.83 volts. Okay. So got it. So VPO1 minus 49.83. Just go through this slide, and if you got any doubts, you can ask me. If it is clear for you, please type 0 on the chat box. We'll move ahead. Next, we shall move ahead to find VPO2. VPO2 is equal to rho L by 2 pi epsilon naught natural log of RO2 divided by RP2 due to the line charge 2. Okay, so RO2 is square root of. So we have to consider only the x and y coordinates here. X and y coordinates 1 square plus 2 square root 5. RP2 consider only the x coordinates, y coordinates in P. It is minus 1 minus 4 square and 2 minus 1 square, that is root 26. So you get VPO2 as minus 118.54 volts. Okay, this is how you got the VPO2. Okay, so now we got VPO1 as minus 49.83 and VPO2 as minus 118.54 volts. Okay, so this is not yet. So we have to solve for VP, but VP is equal to potential due to line charge 1 plus potential due to line charge 2. Okay, so VP1, that is we know VPO1. Okay, so it's nothing but VP1 minus VO1. Okay, that is VO1 is same as VO, VP1 minus VO. Okay, so we got to know this one, and we know this one. We can solve for this one. So VPO1 is equal to VP1 minus VO. Therefore, VP1 is equal to minus 49.83 plus 100, that is equal to 50.16. So any doubts in this one, you can raise, else you can type 0. So this is potential difference between P and O. VPO1 equal to VP1 minus VO1. Yes. Similarly, VPO2 is equal to VP2 minus VO2. Potential difference between P and O due to line charge 2. So VPO2 is equal to VP2 minus VO, that is constant. Okay, so VP2 is equal to VPO2 plus V0. It is minus 118.54 plus 100 minus 18.54. Okay, now we got VP1 plus VP2, that is equal to VP, that is equal to 50.16 minus 18.54, that is equal to 31.61 volts. Okay, so this is how you can find the potential due to an infinite line charge, and you might expect an infinite sheet of charge also. Mm, and you can also get 1 point charge also here. 1 point charge also. So you can find potential due to point charge, or potential due to line charge, potential due to surface charge. Okay. Yes. So what is the expression for E in case of your infinite surface charge? Expression for E in case of surface charge?
Rho S by 2 epsilon naught.
Yes,
Rho S by 2 epsilon naught.
exactly. Rho S by 2 epsilon naught, and it will be in perpendicular. It will be perpendicular, normal to the surface, that is A n cap. Okay. Yes. Using this, you can solve for the potential due to infinite surface charge. Yes. If it is clear for you, please type 0 on the chat box. Okay. So what I will do, I will just stop at this point, and I shall continue in the next class the concept of gradient in potential. Okay, gradient in potential. There is a last concept in this chapter, gradient in potential, and we shall finish it off in the next class. Okay, and then conductors and dielectrics, we shall continue from there. So if it is clear for you, you can type 0 on chat box. If you have got any doubts, you can hang on the chat box. Else you can exit for the next class.